In one of the previous lectures, we had talked about different types of clustering. Clustering, as we discussed, is broadly of two types. One is the hierarchical clustering methods and the other is the partitioning methods. There is a third type which is the overlapping clustering, but then these are not so popular because in this case we have some sort of fuzzy clustering and hence it becomes very difficult to interpret at times. In this talk today, we will be discussing hierarchical clustering in greater detail. We have had some initiation of hierarchical clustering in the previous lectures. Primarily, we had looked at one of the two types of hierarchical clustering, the agglomerative hierarchical method, as opposed to what we will be discussing in greater detail today, the divisive clustering method. Now, both these methods are primarily dependent on the distances that we define between the variables, and we have done this in the last two lectures. So, we will be incorporating those distances as we define the type of clustering either by the agglomerative or by the divisive method. Looking at hierarchical clustering methods, we have seen that this can be of two types: agglomerative hierarchical clustering or divisive hierarchical clustering. We have looked at the agglomerative method in greater detail previously, so we'll make a very quick recapitulation of this method and then go on to the divisive method. Agglomerative method consists of the following. You start from the bottom of the tree or the dendrogram with n clusters of one member each. So at the very beginning we have n different clusters, and then what we do is we decide on a particular type of linkage, which is the distance between the clusters. Having decided on this, we merge the two closest clusters one at a time and go up the tree till all the clusters merge into a single cluster of n members at the top of the tree. This is primarily the agglomerative method. In the divisive method, we do it just in the opposite way. So it's technically the opposite of the agglomerative method, where we start with a single cluster at the top of the tree and continue splitting it into smaller and smaller clusters till the bottom is reached, where there are n clusters with a single member each. Let's look at an example. Suppose this is the top of the tree, and suppose there are 7 individuals in this cluster. So all of the 7 individuals are clustered together at this top of the tree here. And then we have 2 branches coming out from this. So we divide this into 2 branches. Okay? And then again the first branch is divided into 2 further branches. So we go down the tree, and then if you look at the first of these branches, then probably that's the end where we go. But in the second case, maybe this is again divided into further 2 branches. Again, one of this may again be further divided into smaller branches. As for the first of the 2 branches that we had at the first stage, one might go down straight, the other might again be subdivided into 2 further branches. So what we do in this case is, unlike the agglomerative clustering base where we started from the bottom and went up to the top, merging the groups, in this case we started from the top, segregating them one step at a time into 2 different clusters, and went down the tree this way till we reach the bottom, where we now have 7 different individuals into 7 different clusters. Now, what are the advantages and disadvantages of the divisive method? The advantages are, firstly, we start with the maximum information. What is meant by this is we have a single cluster and we know where the individuals within this cluster lie. So initially we do not have separate clusters and having one single individual. A single cluster with all individuals consists of all the information that possibly we can have. Secondly, we need not continue the division till the bottom. So we may want to stop at a certain stage when we have some groups. Say instead of going down to one individual in each cluster, we may stop at the second or third step where we have 3-4 clusters having more than one individual, and maybe we are satisfied with this. So this can somewhat, as we later see, be similar to partitioning. One disadvantage of this method is that even at the first step, there are 2 to the power of n minus 1 ways in which the n individuals can be divided into 2 groups. So you can see that if even n is equal to 5, so if you have 5 individuals, which means 2 to the power of 4, which is 16 minus 1, 15 ways in which the 5 individuals can be divided into 2 groups. This makes computation very difficult, particularly as n becomes larger and larger. So this is the major disadvantage. The other is, because of this disadvantage, what we do is we split the variables in terms of one of the m variables. So we split individuals not in terms of the whole vector but in terms of a single variable, and we refer this as the monothetic method. As opposed to the monothetic method, we have what is referred to as the polythetic method, where we use all m variables simultaneously. But this is much more computationally difficult, as we'll see, and hence if n is large, the monothetic method is primarily used. Let's look at the monothetic methods. So what are the type of methods that we have here? Now again we'll relate this to the type of variables. Suppose all the variables are binary, that is of the present or absent type. What we do is, for each pair of variables j and k, we form the following table. Now it looks similar to what we have done before, but this table is different from what we did before, in the sense that this is in terms of variables and not in terms of individuals r and s. So we have variable j and variable k out of the m variables, and then we look at this over individuals, over the n individuals, and see in how many of these individuals variable j is present as well as variable k is present. That would give us alpha. If variable j is present and k is not present, then the number of such individuals is beta. Similarly, we can define gamma and delta and form a table like this. Based on this table, we next compute what is referred to as a chi-square. This is a chi-square computed on the 2 variables j and k. The numerator gives us n times alpha delta minus beta gamma square, and you can see that the denominator is basically the product of the 4 marginals. So alpha plus beta is the number of individuals who have the characteristic j, and similarly for the others. In this case, of course, the denominator acts as a norming factor, so we are more concerned with the numerator. Now the numerator gives us alpha, delta gives us the proportion, the product of the proportions of those who have actually both j and k and those who do not have j and k, whereas beta and gamma is individuals or who have one of the 2 variables and not both. So if we have both, we have a matching, or we don't have both, we have also a matching. On the other hand, beta and gamma gives us the non-matches. And we get this chi j square value. Next what we do is, so if we have a large value of this, then we say that there is good matching between j and k. For each j, then what we do is, we just take the sum of chi j k square over all possible k and compute what is referred to as Hj. And then we take HL as the maximum of Hj. So if L gives us the maximum of HL, then at the first step we divide by the Lth variable. Put the presence of L in one group and the absence of L in the other group. Okay? And then go on to the next step. Now why do you do this? If you look at the chi-square value here, chi-square jk high means that j and k are very closely related. So it really means that if I divide by k is the same thing as dividing by j, because j segregates, will segregate in the same way as k does. Hence, if these values are high, then the segregation can be done with one of the two variables. Now what we do next is, we look at a single variable and look at its chi-square value with respect to all the other variables. If all this chi-square turns out to be very high, it really means that if we segregate by this variable, then automatically we also segregate by the other variables, and hence we look at the maximum of this Hj and choose that, so that once we do that, we actually have a good separation of the other variables as well. For continuous variables, when we look at the monothetic methods, we first have a split of all possible xj's. So we look at each of the variables, obtain all possible splits into two clusters, say 1 and 2. For each split, we compute the between cluster sum of squares. Okay? How do you get the between cluster sum of squares? It's Bj between cluster 1 and 2 is n1. n1 is the number of members in that cluster, into xj1 bar, that is the mean of that cluster, minus the grand mean square of that, plus n2, which is the number of members in the second cluster, into xj2 bar is the mean of that cluster, minus again the grand mean square. So this is the difference in the sum of squares between the two clusters. And what we do here is that, if you look at this diagram, suppose we want to segregate A, B, C, D, E, F into two clusters. We can do this in several ways. I'll just illustrate three of the ways here. So these three possible illustrations would be that I can segregate them as AB in one cluster and CDEF in another cluster. I can segregate them as ADF in one cluster and BCE in another cluster. I can do the same by segregating BDEF in one cluster and AC in another cluster. So I can have several such splits based on a single variable. In each of these cases, I compute the Bj values. Okay? Bj's for the two clusters that we are forming here. And then at the next step, we choose the Bj among all possible Bj's, which is the maximum. So what we have is, we get for x1 a b1, which is the maximum of all the possible split based on x1. Then we have b2, which is the maximum of all the possible splits based on x2. And similarly for bm. Once we have got this table, what we next do is, we split on the basis of that variable which has the maximum Bj value. So if the third variable has the maximum Bj value, then we at the first step split the single cluster into two clusters on the basis of x3 alone. This is how we go about doing the monothetic method. But as you can see that this method is not foolproof in the sense that we are just basing our judgment on a single variable. On the other hand, in a polythetic method, we usually look at all the variables. But then in that case, it's easier to do if we have continuous variables, because getting a single distance measure based on all the variables, as we have seen previously, is not so easy. So polythetic methods are easier to do for continuous variables. So what we do here is, at each step we split a particular cluster into two clusters, one which we'll call the main group and the other which we'll call the splinter group. For each member in the main group, we calculate its average dissimilarity with the other members of the main group and subtract it from its average dissimilarity with the members of the splinter group. Now what do you mean by this? Now suppose this is the splinter group and suppose this is the main group. So what we look at is the main group on the right hand side. Look at, say, any one of the member, okay? Say B. We calculate the distance of B from A, from E and from C. These three distances we average out. Then we calculate the distance of B from D, H, F and G, and then take the average of those also. And then we take the difference of these two averages. What we can see is that if we are looking at B, in that case its average with A, E and C would be small compared with its average distance from D, H, G and F. So if we take the difference, it's primarily going to be negative. However, if you look at E's average within the group, that is with A, B and C, may not be smaller than its average with E, with D, H, F and G. It's closer to D, probably much closer to D than to B. So this average may not be negative in this case. So you can see that if you look at the main group, some of the differences would come out to be positive, some of the differences will come out as negative. If the difference comes out to be negative, then we can stop the process. If all the members have negative differences, we can stop the process and say that the cluster is now subdivided into the main and the splinter group. Because if all the values come out to be negative, it really means that within that main group, all the individuals are closer to themselves than with the splinter group members. But if some of the values are positive, it really means that that element or that member is closer to the splinter group than to the original group. In this case, we need to shift this individual to the splinter group and then repeat the whole process. We continue with the process till there are no such positive values. So when till all the values come out to be negative, we continue to shift members from the main to the splinter group. And that is how we actually do a polythetic method. But in a polythetic method, when we form the splinter group, usually what we do is we start with the main group, take out a single member which is farthest from the other members and take that to be the splinter group member, and then go on increasing the splinter group members one by one using this technique till all the values or the distance values become negative. Today we discussed the hierarchical clustering methods. We made a very quick recap of the agglomerative clustering method, which we have discussed in a previous lecture, but we went into details of the divisive hierarchical method. We saw that for the divisive method, we can either use the monothetic or the polythetic technique. Monothetic is when we are clustering on the basis of a single variable at a time, and polythetic when we are looking at the whole vector at a single go. Usually monothetic methods are easy to do because you just need to concentrate on a single variable, and computationally it's easier, but polythetic methods are generally more robust in the sense that it gives better clustering, although it has consequently much more complicated calculations. But then, if possible, with given the type of computational facilities that we have these days, polythetic method should be the one used, and monothetic methods primarily can be restricted to variables where we are problems where we have binary variables, because binary variables, monothetic methods with binary variables are usually easier to do.